Hello, students. Welcome to Newton's second law of motion. We are going to introduce Newton's second law of motion, and then we are going to solve related problems. All right. So the first part of Newton's first law of motion deals with the relationship between acceleration of an object and the net force acting on it. So observation tells us that acceleration of an object is directly proportional to the net force acting on it. You can write that as A is directly proportional to, as you can see, this symbol stands for directly proportional to the net force. Okay, so let's look at part 2. Part 2 of Newton's second law of motion tells us that acceleration of an object is inversely proportional to its mass. And that can be written in mathematical equation as follows. A is inversely proportional to mass. Of course, what it means is that the more the mass, the less the acceleration. If the mass is huge, objects won't accelerate that much. That's the implication. And I forgot to mention in the previous slide that when we say acceleration is directly proportional to net force, what we are trying to say is that the more the net force, the more the acceleration. The more the net force, the more the acceleration, and vice versa. That means the less the net force, the less the acceleration. All right, so it is important to understand what we mean by directly proportional to, but also inverse proportional to. All right, so we have two parts to Newton's second law of motion. We also have the third part, which is often neglected, but it is very, very important. It is very, very important to know that the direction of the net force acting on an object is the same as the direction of the acceleration vector. A diagram can help here. So as you can see, here is a situation whereby we have two forces acting on the object, 20 Newton to the right and 10 Newton to the left. If I try to find the net force, I'll find that the net force is 10 Newtons. Remember, we find the net force by adding the vectors. So if I want to find the net force in the x direction, I'll add 20 Newtons. So it's acting to the right. I'll add plus 20 Newtons. And then I see that I have 10 Newtons acting to the left. So I'm going to add minus 10 Newtons, minus because it's acting to the left. Now the result here will be, actually this means it's 20 Newtons minus 10 Newtons. So 20 Newtons minus 10 Newtons. The result is 10 Newtons with a plus sign here, meaning that our net force is acting to the right. Now, according to this part of Newton's second law of motion, if I know that the direction of net force is to the right, indicated the plus sign here, then the acceleration is also pointing to the right. So our acceleration, as you can see here, is also pointing to the right. All right. All right. So we can combine what we have learned in the previous slides. We have learned that acceleration is directly proportional to the net force. And of course, the direction of the acceleration is the same as the direction of the net force. Usually, we like to write net force by using this sigma notation, this one. In this case, we can write acceleration is directly proportional to the net force. Instead of writing net, we just write this symbol here, meaning that that's net force acting on the object. Part 2, we learned that acceleration is inversely proportional to the mass of an object here. And then we can combine part 1 and 2 into one equation. And we are going to have this connection, which tells us that acceleration on the acceleration of an object is directly proportional to the net force acting on the object. And also it is inversely proportional to the mass of the object. So this equation takes care of all the parts we have seen. And as you can see, the direction of acceleration is the same as the direction of the net force. So we can see here, we are trying to actually find a better equation. So with good units or with appropriate units, we can convert our original equation here into something nicer. When we choose the units of acceleration as meters per second squared and the units of the force in newtons, the mass is in kilograms, then we can say that acceleration is equal to net force over mass. So we replace this sign here is replaced now by actually an equal to sign here. Once we choose appropriate units, we can now go for an equal to sign instead of a directly proportional to sign. If we rewrite this equation here, if we rewrite it, we can rewrite it so that it looks like a linear equation, not fractional equation. By cross multiplying A times M, 1 times net force, you're going to end up with this equation. You are going to see this equation is very common in textbooks. They just say net force is equal to mass times acceleration. Remember, the formula says net force, not just force equal to mass times acceleration. This is not a better way to state this. You must emphasize that it is the net force. The net force is very, very important there. This is not a better way to state Newton's second law mathematically. All right. So let's see. Now, this is an example that we can try to apply our Newton's second law of motion. For example, here we have a box that is sitting on the floor. Well, it's actually moving, it's accelerating actually, but we just don't know the acceleration, but sitting on the horizontal floor. Of course, we know there are forces acting on this 2 kilogram object. There is a gravitational force acting downward, and of course, there's a normal force acting upward. But usually these forces cancel out because they balance. There's no acceleration in the vertical direction. So these forces do not take part in our calculations. What the forces that are taking part in our calculations are the horizontal forces, the 20 Newton force and the 10 Newton force to the left. Now, once we know all the forces acting on the object, then we can find the net force acting on the 2 kilogram mass. Now, to answer our question, what is the acceleration of our 2 kilogram mass? We are going to write Newton's second law of motion in the X direction because we are dealing with the X axis, the horizontal direction. Now, acceleration in the X direction will be net force in the X direction divided by the mass. This is where we are. And then we have to find out the net force acting on the 2 kilogram mass. Remember, we choose, oftentimes we choose the right as positive and the left as negative, but we can do the opposite. In this case, we are not doing the opposite anyway. We are doing the traditional one. Right is positive. Anything pointing to the left picks a negative sign. Now, if we do the algebraic sum here, taking care of the signs, we are going to have our net force here as 10 newtons and the mass is 2 kilograms. Now here we have acceleration in the X direction is 10 newtons divided by 2 kilograms. And that will take us to 2 into 10, it's 5. And on top, we have newtons slash a kilogram. This tells us that our acceleration is 5 Newton per kilogram, but we do not talk about a Newton per kilogram as a unit of acceleration. What we usually talk about is a meter per second squared. Now we are going to write this as AX equal to 5 m slash s squared, meaning that it means that 1 Newton per kilogram is actually equal to 1 meters per second squared by definition. We have defined this unit as a meter per second squared. Now, from now onwards, each time we see a Newton per kilogram, we are going to replace it with a meter per second squared. This shows that our acceleration is actually 5 meters per second squared. Let's look at another example. This other example, we are given acceleration as 5 meters per second squared. We are given the applied force 30 newtons, and where there is a force that is acting to the left, that could probably be due to friction. Now we have to find out what is that force. If you are given this question, given the acceleration is 5 meters per second squared to the right, as you can see, what would be the value of force F? Now, to answer this question, we need to understand that we have to apply Newton's second law. Newton's second law in the x direction will tell us that the net force in the x direction is mass times acceleration in the x direction. We are here. Now, the net force in the x direction can be found, but just as a statement without a number, because we don't have the F. Remember, we choose right as positive and left as negative. So we have our plus 30 newtons here, and then plus minus F, because F is acting to the left, equal to our mass becomes 4 kilograms here, and our acceleration becomes 5 meters per second squared. Now this, all this becomes now 30 newtons minus F equal to 4 times 5 is 20 kilogram meter per second squared. Now a kilogram meter per second squared is actually a Newton from our definition. A kilogram meter per second squared is a Newton, or this is just a Newton. It's like mass times acceleration, so it's a Newton. Now we have 30 newtons minus F equal to 20 newtons. From here, we can find F as 10 newtons. We can find F as our 10 newtons. That's our answer there. So the force that we were looking for in this problem, this force actually is actually 10 newtons. Let's look at the another question. Let's look at another question. This one. A 10 kilogram ball is in free fall near the Earth's surface, where G is usually 9.8 meters per second squared. What is the excuse me? What is the net force acting on it? Remember, objects in free fall, the only force acting on them is gravitational force. When objects are in free fall, the only force acting on them is gravitational force. Then we have to apply Newton's second law to that situation. It is always important to draw a force diagram. A force diagram shows all forces acting on the object. You draw all the forces acting on the object. That will help us to find the net force on the object. Let's see. We are here. Now, since the object is in free fall, the only force is gravitational force here, Fg. And before I apply the second law, this equation here, before I apply this equation, I need to make sure that I have the I have the coordinate right. So anything up will be positive, anything pointing down will be negative. I can do that. So positive up, down is negative. So when I apply my second law, I have to make sure that up is positive, down is negative. I'll try to do the other way around later. Now, net force in the y direction will be equal to 10 kilogram times minus 9.8 meters per second squared. I'm here. The reason I'm saying minus 9.8 meters per second squared for a acceleration in the y direction is because I see that acceleration in the downward is given negative because I chose negative here. Anything pointing down is negative. So my acceleration in the y direction will have a minus there because I chose down as negative. Now, if I continue here, 10 kilogram times 9.8, I get 98 kilograms meters per second squared. And remember, a kilogram meters per second squared is actually a Newton. Now, I can now substitute because I know the only force acting in the y direction is Fg, but it has a negative sign here. Now minus Fg equal to minus 98 Newtons. That means if I divide both sides by -1, I'm going to get Fg is equal to 98 Newtons. Therefore, the magnitude or the Fg value that I was looking for is 98 Newtons. I can also solve the problem using a different coordinate system. Now I'm going to use up as negative, down as positive. Remember, we don't have to always say up is positive, down is negative. We can actually do the opposite. We can do whatever we want as long as we are consistent with our choice of coordinate. So I have minus negative up and down is positive. Then when I try to find the net force acting on this mass, I will apply the second law here, which says net force in the y direction is equal to mass times acceleration in the y direction. I'm now going to ask myself, what is the net force in the y direction? The net force in the y direction is just Fg, but it has a plus sign here. As you can see, it has a plus sign here because I chose down, anything pointing down as positive. It has a plus sign there. So plus Fg. Mass is a scalar quantity. It will just be 10 kilograms. Acceleration in the y direction. Acceleration has to be like a vector. It has a direction. But I chose down as positive. In that case, I'm going to say my acceleration downward will be plus 9.8 meters per second squared. The positive sign here indicates that I'm consistent with the choice of my coordinate, plus 9.8 meters per second squared. Now, Fg will be equal to 10 kilograms times 9.8 meters per second squared. That will give me 98 kilograms meters squared. Fg will be 98 Newtons because the kilogram meter per second squared is actually a Newton. Therefore, Fg is equal to plus 98 Newtons. In general, gravitational force is given by Fg is equal to mg. You're going to see that most of the time, we are going to say gravitational force is equal to mg. As you can see, it works. If you multiply the mass times g, you always get the same answer, regardless of the choice of coordinate. You get 98 Newtons. Therefore, the gravitational attraction on an object, 10 kilogram ball, the gravitational attraction downward will just be mg, simply mg. And this mg gives us 98 Newtons as our answer. But we carefully applied Newton's second law of motion. Thank you so much for listening. If you have any questions, please reach out to me. Bye-bye.